pick up the second semester, we want to start talking about modern atomic theory. Modern atomic theory is going to pick up where we left off with atomic theory in the fall semester, and get into what's happening with the electrons, and start to get us into electron configurations. I like to use this picture a lot because a lot of the scientists that we're going to be talking about in this chapter were all alive at the same time and all working in together on these type of topics. They were all working at the same time period and were working through a lot of the same concepts separately, but many of them will come up with many of the topics we will discuss in this chapter, including some of the ones that you probably recognize here, like Albert Einstein, our one female scientist in the picture, Marie Curie, and then we'll also see people like Schrodinger, Pauli, Heisenberg, Bohr, de Broglie, and Planck, a number of these scientists who are all involved in the formation of quantum mechanics, which describes how the electron behaves in the atom. Quickly, a review of the atomic models. John Dalton gave us the first model of the atom, and he said the atom was a uniform sphere that could not be broken down into any smaller parts. J.J. Thomson did the cathode ray tube experiment. That cathode ray tube experiment showed that we had an electron. We eventually showed that we have a proton. This disproves Dalton's model of the atom, and we now have the plum pudding or chocolate chip cookie model of the atom. And then we finished in the fall with Ernest Rutherford and the gold foil experiment. Gold foil experiment showed us that we have a nucleus in the atom by barraging the atom with high energy alpha particles, which are 2 protons, 2 neutrons, and having them travel straight through most of the time, but a few times bounce back towards the source. The fact that they bounce back to the source so that there's a very small, very massive, positive part to the atom, which becomes known as the nucleus. We didn't discuss at the time what was happening with the electrons because that part was not really well explained in Rutherford's planetary model. Rutherford's model had a number of problems with it. Key one was that there was no clear explanation for what was happening with the electrons. The original idea was that we had something like the planets, with the sun being our nucleus and the planets going around the outside in these orbits, these paths, as the electrons. However, there's a major problem with that idea, and that is the fact that the electron is negatively charged and the proton is positively charged. We know that negative and positives attract one another. So, because of this attraction, incredibly small distance, the electron should collapse into the nucleus, causing the atom to fall apart. Anytime those electrons lose any little bit of energy, they would start to collapse towards the nucleus and eventually would collapse completely into the nucleus under that model. So it doesn't work that way, but we really don't have a better explanation at the time for what's going on with the electrons. To understand a better explanation of what's going on with electrons, we need to talk about some science of some other concepts before we get into specifically what's happening with the electron. We're going to start by looking at waves. Waves have unique properties, and we want to talk about the basic properties of waves because we'll see that electrons end up behaving both as particles and waves at the same time. Waves have 3 basic properties. The first one is wavelength. Wavelength is the distance between 2 of the same points in a set of waves. We give this the Greek symbol lambda, and it's going to have the units of meters, some form of meters, because it is a distance. So if you go from the peak of a wave to the peak of the next wave, trough of a wave to the trough of the next wave, or from where it starts to where it begins again, that would be the wavelength. The second property is amplitude. Amplitude is the height or depth of a wave, how tall the wave is going to be or how deep the wave is going to be. Those are the same. This will also be in meters because it's a height or depth. And we'll give them the symbol A. So if we look at this picture here, we have 5 possible letters that we can choose from. Look at this picture and decide which one is the wavelength and which one is the amplitude. Now when you look at this for a minute, you see a number of possibilities for wavelength. It could be A, E, or C. The correct answer here is A. A is the wavelength here, from the peak of one to the peak of the next. E is half a wavelength from the peak of one to the trough of the next. C is half a wavelength. It just covers the peak. It does not cover the trough. So A is the only one here that is a wavelength. For amplitude, the correct answer is D. D is one amplitude. It can be either the depth or the height of a wave. B in this case, because it's the other one that could be similar, but B is two amplitudes. It's the depth plus the height, so you have twice the amplitude in B. Third property is known as frequency. Frequency is the number of waves that pass a certain point in a given amount of time. Waves travel at a constant speed. For example, if you have a wave of light or electromagnetic energy, light being one form of that, it travels at the speed of light, 300 million meters per second. We give it the symbol for frequency of the Greek letter nu, which is a sort of curvy V. It is going to be in either waves per second or hertz. Those are the general units that we will be looking at. So our two possible units here, waves per second or hertz. Hertz is another way of doing cycles per second. You can't draw frequency on a wave. Frequency is something that is a property of a wave, but can't be drawn onto the picture. The closer the peaks are together, the shorter the wavelength, the larger the frequency is going to be, or vice versa. So when we talk about waves, a couple of key properties, and the key one to notice is the relationship between wavelength and frequency. It is an indirect relationship, meaning as one goes up, the other goes down. So the higher the frequency, the lower the wavelength, the shorter the wavelength. The longer the wavelength, the lower the frequency, because waves travel at a constant speed. The equation that actually comes out of this is velocity of light, which is the letter C, or for any general wave, velocity equals frequency times wavelength. The speed at which the wave travels equals the frequency times the wavelength. They're an indirect relationship. Now, light is unique. Light was looked at by two main scientists, Max Planck and Albert Einstein. Max Planck found that there was a relationship between the energy of an atom and the wavelength of the light that emitted when it was hot. Think about a piece of metal. If you heat it up, it starts to glow a color. It could be red, it could be another color, depending on the type of metal. That color of light that's being given off is related to the energy in the atom. So Max Planck was showing that there was some sort of relationship between light and energy. Albert Einstein gave us a suggestion that light was actually made up of something called photons, little packets of energy that traveled through space as a wave. So they could have both sort of properties of a wave and a particle at the same time. So the light that we see with our eyes and all electromagnetic radiation is actually photons, little particles of energy that travel as waves. And we'll see this has a very direct relationship to the electron. In the next video, we'll get into the electromagnetic spectrum and the difference of all the different types of energies, frequency, and wavelengths that deal with light and all other types of radiation.